November 26, 2012, the Center for Nanoscience and Engineering at the IISc. As the day begins, 20 selected PhD scholars and young faculty members from across India gather to learn micro and nano fabrication fundamentals under INUP, or the Indian Nanoelectronics Users Program. The participants form 4 groups, each with a different device to fabricate. One of these devices is the cantilever. During orientation, participants are introduced to facilities at Sense's National Nanofabrication Center and the potential to conduct hands-on research. Then, a detailed explanation of clean room protocols to follow over the next 2 days is presented. NNFC experts also present an overview of the fabrication and characterization processes the teams will deploy. After orientation, the teams proceed to the NNFC clean room. Here on, we will follow the cantilever group. At the outset, let's define the object our team will fabricate, namely a MEMS cantilever. A cantilever is a projecting structure such as a beam, which is supported at one end only. It may carry a load at the free tip or along its length. Next, let's identify the broad microfabrication technology we shall employ, which is surface micromachining. This approach requires a silicon-on-insulator or SOI wafer, which is a 3-layer material stack composed of the following. On top, a mechanically active device layer made of prime quality silicon. Intermediately, a buried sacrificial layer of silicon dioxide or box. This electrically insulating intermediate layer is selectively etched. At the bottom, a support wafer or handle of bulk silicon. Our SOI wafer has a 1 micron thick silicon dioxide layer buried under 200 nanometers of silicon layer. We initiate MEMS cantilever fabrication by cleaning the SOI wafer. This is done in the wet etch bay. First, we place the samples in a wafer holder and dip it in the piranha bath of the wet bench. The samples are kept in the solution for 10 minutes. The piranha solution removes any organic and metallic contaminants from wafer surfaces. The solution is prepared by mixing sulfuric acid and hydrogen peroxide in a 9:1 ratio by volume. 10 minutes later, we remove the samples and rinse thoroughly with deionized water. This is followed by blow drying the samples with nitrogen. The samples are now clean and ready for the next step of photolithography. For the next step, we move to the lithography bay, which has a cleanliness level of class 100. Here, we shall transfer cantilever patterns from a glass mask onto the cleaned wafers. First, we dehydrate the samples at 250 degrees Celsius for 10 minutes to remove surface moisture. Next, we spin coat the wafer's device layer with photosensitive resist of nearly 1 micron thickness. Rapid spinning causes the liquid photoresist to spread uniformly on the wafer surface due to centrifugal forces. In this three-dimensional model, we see that the photoresist layer covers the entire device layer in even thickness. We now move the resist-coated samples for soft baking on an adjacent table. Soft baking is done at 95 degrees Celsius to evaporate the solvents in the photoresist. The soft-baked photoresist will not stick to the glass mask during the next step. In a similar way, we process the entire batch of wafers. We are now ready for cantilever pattern transfer, which takes place on a separate workstation. NNFC has an EVG double-sided mask aligner. First, we pick a cantilever mask prefabricated especially for INUP from our mask library. The mask consists of transparent and opaque parts that define a desired pattern. When we place this mask over the resist-coated sample and expose to UV light, cross-link bonds in the resist are broken. We first load the samples onto the mask aligner tray. Then we place the mask on the wafer. Now the assembly is ready for ultraviolet exposure. UV light exposure is done at predefined energy levels specified in millijoules per centimeter square. After UV exposure, we must develop the pattern on the sample's photoresist. For this, a specified developing solution is taken in a Petri dish. Next, we place the UV-exposed samples in the developing solution. The photoresist now contains exposed and unexposed areas. The exposed part is soluble in the developing solution. Therefore, it dissolves, leaving behind a replica of the mask pattern. Once the pattern is developed, the sample is rinsed with DI water and given a nitrogen blow dry. We have now created the cantilever pattern on our sample's photoresist layer. To confirm, we make a quick microscopic inspection. The cantilever pattern shows up clearly on the microscope's display screen. The next stage of cantilever fabrication takes place in the dry etch bay. Here we employ the ICP RIE fluorine chemistry tool to etch the exposed device layer. These are our samples from photolithography. First, we apply formalin oil on a large carrier wafer to prepare a sticky base for the samples. Next, we place the samples on the carrier wafer. We now load the samples into the RIE station load lock chamber. Next, using the graphical user interface of the station, we create a vacuum in the load lock. Then the samples are transported into the RIE main chamber. Gases start flowing inside the chamber at specified flow rates and temperature. Plasma strikes when appropriate conditions are reached. For our device layer of 200 nanometers. We have specified an etching time of 2 minutes. Let's understand in depth what happens inside the system. We are now watching the sample in an ions and plasma environment. Fluorine ions in the plasma start etching the exposed silicon following a chemical reaction. After etching, we unload the samples from the RIE equipment. Since the bottom surface of the sample has formalin oil, we wipe it away with lint-free cloth. We now have the cantilever pattern on the device and photoresist layers. Again, we take a quick look through the microscope. Once more, we see clear images of the cantilever pattern. To remove the photoresist layer, we return to the wet etch bay. Here, we prepare a Piranha solution of sulfuric acid and hydrogen peroxide in a ratio of 3:1 by volume in a glass Petri dish. The samples are then placed inside the solution. The liberated color confirms removal of the resist from the sample surface. This takes 10 minutes. Here, the Piranha solution attacks the resist material, removing it from the wafer surface. Consequently, the samples now contain a patterned device layer over oxide. After photoresist removal, samples are rinsed with deionized water and blow-dried with nitrogen. Next, we come to the critical step of cantilever release using wet etch. Here, the buried silicon dioxide layer will be etched out with buffered hydrofluoric acid. The BHF solution has been previously prepared at the NNFC to etch at the desired rate. Since the anchor regions are much larger than the beam regions, some oxide remains intact under the anchors after isotropic wet etch, creating a suspended cantilever anchored to the substrate. This is followed by a rinse with DI water and isopropyl alcohol. Here, care is taken to let samples remain in liquid. Otherwise, chances of stiction or cantilevers sticking to the substrate are high. To inspect the released cantilevers, we move to the lithography bay, which has the Leica microscope. The inspection must be carried out on submerged wafers from the previous step to avoid stiction. The release is confirmed by noticing that the cantilever and the substrate require differential focusing. Next, we advance to the step of drying the wafers in supercritical dryer equipment. First, we remove the top lid of the dryer to expose its inner chamber. Next, we fill the CPD chamber with isopropyl alcohol to immerse the special sample basket. At this stage, exposure of samples to air increases chances of stiction. So we transfer submerged samples along with IPA into the basket with a large spatula. Then we complete the basket assembly.